And I bet I know where the rest of you are. Tucked up in bed. No doubt. Alright, so week 6. You thought just because you'd finished assignment 1 things were going to get easier. No! This week we have a practice exam, although that's like flogging you with a wet lettuce or something. Because the problems are pretty easy. Why am I getting feedback? Am I? Where's that coming from? Don't know. Oh well. We'll keep going. I can't seem to get rid of it. Oh, now it's gone. Good. Yeah, practice break exam this week. I think I said last week there was only 1 problem, but I decided to make you work twice as hard, so there are 2 problems to solve. You bastard. But it's not worth much, so it doesn't matter. Assignment 2, I'll sort that out this week. And today I want to talk about queues and recursion. There's a few little sections about programming techniques that I'll gradually get to, but today's one will be on recursion in a particular context. Alright, here's some stats about assignment 1. Last week there were 465 people enrolled in the course. This week there seem to be 450. I guess the pressure of assignment 1 must have got to them. Anyway, 390 people have submitted so far. I guess the rest of you will eventually. Someone knows about time management and they submitted on August the 20th. You beauty. I didn't check since I came in, but the latest submission I saw was 10 minutes before the lecture time. And of course, the number of submissions between midnight last night and this morning was 218. And they ran all through the night, starting at midnight. I think there was a clutch of people who decided to finish at midnight, but the rest of you decided to sit up through the night, just like that video.
Can you graph them?
Huh?
Can you graph them?
Can I what?
Can you put them on a graph?
Oh yeah, I could. I didn't have time. Setting up these prac exams is tedious. That's taken a lot of time. And it probably won't work, I can guarantee it. Who's in a Monday lab? Good, you'll be the guinea pigs to see if it works properly. Alright, how many don't compile? I don't know, because I haven't had a chance to test them yet. But we shall see. Alright, here's another famous nerd. Without him, our lives would be, I suspect, very different. Anyone? Correct. You're obviously looking at something else, or maybe you just know. Yeah, Tim Berners-Lee. Sir Tim Berners-Lee to you, in fact. So what did he do? He invented the web. That's a nice claim to have next to your name. Basically, what his contributions were, technically, the notion of distributed hypertext. Now, I mentioned a couple of weeks ago that Doug Engelbart had this idea, but Tim Berners-Lee managed to get it at just the right point in history where it could take off. So the idea was, what he actually set out to do, he was a software engineer at CERN, which is that big physics lab in Switzerland, probably related to that giant particle accelerator thingy. He wanted to set things up so that all the scientists in the lab could share documents. You know, nowadays we just take all this stuff for granted, but back in 1990 when he did this work, people had to email documents around if they wanted to share them, whatever. At least they could email them. That was a start. So the idea was there were all these documents, some are in Word format, some are in PDF, blah, blah, blah. Wanted to be able to go from one document to another document to another document. Like I said, something that we all take for granted. If you want to do that, you need a way of specifying where the other document is. So he came up with the syntax for URLs. And he also, and once you've decided where you want to get a document from, you've got to serve it. He also came up with the transfer protocol to get the document onto your computer and into your web browser. So, yeah, he came up with those ideas. They set them up at CERN. A few other people saw them, thought it was a good idea, and this is where we are today. And he got a knighthood for that in 2004. Currently he's actually hammering on about, so the idea of hyperlinks is nice. You're just saying this document relates to this document. I simply want to go from this document to this other document. His other idea is the notion of the semantic web, where rather than just having hard links, you can actually specify what kind of documents you want to go to, rather than just saying, all right, here's a link, bang, go there. So that's something he's been getting into for quite a while, in fact, probably since around 2000. All right, let's get on with this. So, last time I talked about stacks, last in, first out protocol. Today I want to talk about queues, which in their simplest form, first in, first out protocol, basic operations, stick something on the queue, goes at the back of the queue, you know, like what happens when you go to Subway or whatever, and DQ takes it off the front of the queue. So the first thing that went into the queue is the oldest thing, you know, the thing that's been in the queue the longest is the first thing that comes out. Here's another bunch of standard operations that we might have on queues. So let's take a look at implementation of a queue, and in particular I wanted to use an array representation. A list is dead easy. If you want to have a linked list for a queue, you simply have a queue representation that's got a pointer to the first element in the list and a pointer to the last element in the list. When you DQ, you take off the first element. When you enqueue, you add it after the last element. That's what it is. It's the phone. There's nobody there. Could have been Donald Trump, you never know, if I was unlucky. All right, so let's take a look. I'll go straight to the implementation. All of the pre and post conditions, I won't bother with them, but basically it's very similar to the kind of things that we dealt with stacks. We want, if a function has an argument which is a queue, we want it to be a valid queue. If we add an item onto a queue, then that item appears in the queue. You know, all those kind of conditions hold. Okay, so a new queue. All right, here's our queue representation, slightly more complicated than some of the other ones we've been looking at. Because I'm doing it as an array, I need to know how large the array is, and I'm going to dynamically allocate it. I need to know, you know, it's all very well to know there are X slots in the array. How many of those slots are actually occupied by things that are on the queue? So n items is going to tell me that. And then we got an index to the first element in the queue, the one that's going to come off when I do a DQ, and the tail of the queue is another index which tells me where the last element is, and I can use that to work out where is the next spot in the queue that I want to add an item to. And of course the data itself is an array of items declared here as a pointer because I haven't allocated it yet. Alright, so setting up a new queue, we have to malloc space for a queue representation, and of course we go, as far as the outside world is concerned, they're going to see this as a pointer to a queue rep, so all they see is the pointer. So obviously we need to make one of these things. And we'll do the cheap and nasty check. So that gives us one of those objects. Then we have to set it up. How big is it? What's the size going to be? Well, we're told how many slots we want to put in the queue as the parameter to new queue. So all the other new things we've looked at, new list, new stack, didn't have any parameters. This one does. And so the size of this new queue is going to be length. The number of items, well, it's initially empty, so there aren't any. And the location of the head and tail, well, we may as well put them at 0. Put them both at 0 for the time being. Right, so that's most of it. The other thing we have to do, we need to make an array, so we need to malloc that, and new data. And the malloc is going to look like length, which is the number of items, and each item is the size of an item. And we want to make sure that actually worked as well. And having done that, we've got the queue completely set up. The array is full of garbage. We don't care because we're not going to look at anything because we know that there are 0 items in the queue. So we just return a pointer to that. So that's a little bit more set up than most of the other data structures we've looked at. We'll see data structures in the future that are even more complex to set up. All right. If we decide that we're finished with a queue and we want to free up the memory, what to do? Two things have been malloced, so we need to free up both of those things. So I guess first thing we could check is to make sure that we have a real queue. That doesn't actually guarantee us that, but at least it guarantees us that we've got a valid pointer. We want to free up the data, so free up the array that we allocated initially, and then we can free up the rest of the structure. So that's all that's required there. Okay. Let's see, what shall I do? Let's take a look at show, or even n items and so on. All right, so n items is dead simple. We just extract the value from the queue, and I guess if we really want to be paranoid, we can make sure is empty. We can do even more simply. We can just say and that'll do the check that the queue is valid for us. All right, so displaying a queue. All right, so we know the index of the first item, we know the index of the last item. The trick with implementing something like this as an array is that we insert the first item in the first slot in the array, next item in the next slot, next item in the next slot, So we're gradually filling up the array, but we're not necessarily going to fill it up. That is an issue that we have to worry about. But likely we'll put a few things on the queue and then we'll take some things off the front of the queue. So there's going to be empty space at the start. We'll keep adding things at the end, and eventually we're going to reach the end of the array. That doesn't mean we've run out of space and we can't add anything else, because there's spaces at the start of the array where we free things up, so we need to go back to the start. So the indexes, head and tail, are things that basically go circularly, if that's a word, around the array. So working out what to do here, we need to start from the head of the queue, and we need to go until we reach the tail. Now that might involve starting here and just going da 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 da, and there's the tail. But it might involve starting here, going to the end of the array, then having to go back to the start and da da da, and there's the tail. So it's quite possible that tail might be a smaller index than head if we wrap things around enough. So let's have an index. How to structure this? No, I'll do it that way. Right, that would work, assuming Q's at the start of the head is at the start and tail is somewhere along the array. Well, sorry, head is here and tail is somewhere back there. But that's not going to work if we have to wrap around. So can anyone suggest what to do to make this index, to ensure that this index, starting from here, goes da da da, reaches the end of the array, then goes back to the start?
Modulo by the size of the array.
Yeah. So we simply take mod size of the array. Well, let me think. Where's the best place to do that? Yeah, I guess I could do that. And what's the size of the array? It's the size of the queue. Okay, hopefully that will work. So let's say the head is 8 and the tail is 1, and the whole thing is length 10. So we go 8, we go 9, we add 1, becomes 10, we take mod 10, we go back to 0. So that ought to do the trick of circulating around the list. And of course, for each of those things, we want to print. And let's say, for the sake of argument, we know that our items are simple integers. And the one we want is the one in the ith position. So I gives the current position in the array. Okay. Someone should say, "Oi, but you're going to get narrow at the end." No, I'm not. Because the stopping condition is that I has reached the tail of the queue. It hasn't actually done anything with the tail element. So conveniently, I can just, and I might want to call that printf. So I stopped, that for loop stopped when I'd reached the end of the queue, and I can print out the final item. Any problems with that? I can see a problem. Yep.
What if the queue is empty?
Yeah, exactly. So if the queue's empty, we got an issue. I don't think we'll have a problem here. We won't execute the for loop at all, but we will have a problem with printing out the final data item. So one way to handle that, I could simply put an if statement there and only print if f items wasn't true. But a convenient way to deal with these kind of issues is to basically check at the start that we don't have some sort of boundary case like empty or full, and just handle it at that point. So if the number of items is equal to 0, well, there's really nothing to print. Although we might want to print a new, I'm not sure. In fact, let's actually print something. And then give up. Well, that's being a bit naughty, isn't it? Putting too much on one line. Alternatively, I could easily make an else and just put the for loop in the other printf in the else part. But dealing with stuff up front and sort of getting it out of the way makes the rest of the code a little bit simpler. So I've handled the empty Q case, done, go on and deal with the non-empty Q case.
It should be printf up.
It should be what? Oh yeah, thanks. Wrong language. Yep. Lucky I didn't write echo. That'd be a bit of a giveaway. Alright, so that should display the queue whether it's empty or non-empty, hopefully. Alright, so we can make a new empty queue, we can drop a queue, we need to add stuff onto the queue, so let's implement that for a start. Make sure that works, because now we can display queues. Well, hopefully show queue is actually working, otherwise we got a problem. So enqueue, what do we need to do? Items are added at the tail of the queue, and they're added at the tail of the queue. We know where the tail index always tells us where the last item is. So what we need to do, increment tail by 1, and into that position we put the new item. Now of course we have this issue that the current value of tail might be the very last item in the queue, in which case we'd have to wrap round to the start. So we need that +1 mod size again. The other issue in this implementation of queues is that it might fill up. And if it fills up, then we have a problem. A couple of ways you could handle that. You could just reject, just do nothing. So check if the queue is full and just don't add the next item silently without telling the user. We'd have to do that given that this is a void parameter, a void function. Another way of handling it, maybe we make enqueue return a status value. Yes, I was successfully able to enqueue this item, or no, I wasn't, and then it's up to the user to deal with that. Or we could take the lazy way and just assert that the queue isn't already full. That at least won't crash our code in the sense that the code won't do something weird. It's a kind of controlled crash, if you like. So if queue, the number of items in the queue has to be less than the queue size, otherwise we can't enqueue an item. If that's true, let's do a bit at a time. So the location where we're going to put the next item is I was going to do that, but that wouldn't be such a good idea. I would probably want to do something like maybe I won't bother with an eye. I'll just do it everything on the tail. So move the tail along to the next location, and if the next location happens to be off the end of the array, go back to the start. And then into that particular location, we copy the new item. Oops. So hopefully that will handle that. Since that was so simple, let's write dequeue as well. You don't want people trying to dequeue from an empty queue, so we could add the assertion that n items is greater than 0. Notice these assertions are going to print error messages that reveal information about the internal structure of our queue, so maybe they're not such a great way to handle things. If you don't want users to know what your queue looks like internally. But for development purposes, they're okay. Alright, so what to do here? I would suggest that we can grab a copy of the current head item. And then we can advance the head pointer. So something like that. Yeah. And of course we have to return the item that we just dequeued, so we return it. Alright, so that might even be everything. Wow, what a miracle. Chance of that compiling are pretty close to 0, but we'll try that in a minute. Have I got a makefile? No, I don't. And because I'm sure it's going to crash, I'll compile it with GDB turned on, just in case. Alright, so let's see. I think I had... Whoops, not called list, it's called queue. Right, so if I want to build my queue tester, I need to have compiled the main program, which happens to live in test.c, and I need to have a compiled version of the QADT. And hopefully Make's going to be smart enough to know what to do there. Similarly, I need to tell it that test.o comes from test.c and depends also on q.h. So if I change q.h, I need to recompile, I need to recreate test.o. And the q.o file comes from q.c, and it also hash includes q.h. So if I change q.h, I'll need to recompile q.c to produce the new q.o. And it should be smart enough to work out the compilation steps required there. I guess we can have a cleanup thing. The -f option on remove basically tells remove, if the files that I'm mentioning don't exist, don't worry about it, just ignore it, otherwise it'll complain about you're trying to remove non-existent files. So if there was no TQ or if there were no .o files, it would just be quiet rather than complaining about them. Alright. Beautiful. Good. Alright, so that was in test.c. So that was because my initial version of queues that I was playing with used a list, so I didn't need to specify a size. Here, since we're doing not very much, let's make a small queue. That assert's probably not necessary because new queue does all that kind of checking for us, so we're guaranteed to get something back. Alright, so what to do? Oops. Good thing to do initially is to see if you can print the initially empty queue. That'll do two things. It'll help you check whether your show queue function is sensible and works for an empty queue. It'll also help you check whether, well, to some extent, whether the new queue function actually did something sensible. And let's try one DQ. Remember, DQ returns the item at the front of the queue. So that's part of what we need to check. Need to make sure the queue looks sensible after that, but we also need to make sure that we actually return the right thing. Okay. That looks kind of plausible. Let's see. It wasn't called show queue, was it? What was it called? It was called just show. Fair enough. What's the chance? Are you going to get a core dump, or is it just going to work? Let's see. Oi. Why didn't it make TQ? How interesting. Maybe Make's not as smart as I thought. Alright. Beautiful. What? Oh, of course. Good. Someone should have pointed that out while I was writing the functions. Well done, assert. NQ and DQ, what did I do with N items? I forgot to do anything with them. So for an NQ, obviously we're adding an extra item. And when we're DQing, we're removing an item. So beautiful. Oh, is it? Where'd that 0 come from? Interesting. Interesting. I didn't queue a 0. Ah, okay. I think I need to reevaluate my definition of what tail is somehow. Alright, so initially tail is set to 0. The first thing I do is I increment tail and then insert the new item at that location. That's going to work alright as long as there's a real tail. But we've got this initial case where the queue is empty. We set tail to 0, but that's not kind of a real value. I guess we could set it initially to -1 and then leave that code there. The other option would be to have an explicit check for the queue being empty and then setting tail appropriately. So I guess initially we can set head to 0, that's going to be true, and we could initially set tail to -1, which looks a bit counterintuitive, and it's a little bit nasty because we're relying on that in another part of the code. So there's this dependency between those two parts of the code. They're not too far apart, and it might be easier from a maintenance point of view to actually have the explicit test for empty inside NQ, but I'll be lazy and do it that way. Probably crash it anyway, so doesn't matter. Alright, that looks a bit more plausible. So an empty Q, Q of 5, Q of 3 added, and we pop, when we DQ we get 5, which is the last thing we added. Alright, let's do a bit more stress testing. So I'm old school, I don't declare my loop variables inside the loop. So we didn't prove very well. We proved a little bit, at least when the queue, we add a couple of items and head is greater than tail and everything works. Let's see what happens if we have to do a little bit of wrapping around. So let's add something onto the queue and then actually, do I want to do that? No, let's just test it out first. Where we're going to overflow the queue. Now we can leave that code there. Let's see, make sure it handles that case properly. Oh yeah, I started from 0. Whew. Thought I'd put the bug back. Alright, so that's fine. We filled it up, and then because we ran out of room in the queue, we failed. We couldn't in-queue anything else. Let's remove it. After every third iteration of this loop, let's remove one of the items from the queue. We're probably still going to overflow it. Maybe we're not. We might bother, should we? We really ought to check what we actually got back from DQ. Notice that when you in C, if you've got a function that's supposed to return something, you can just call that function and do nothing with the return value. So at this point, we're really just interested in getting stuff off the queue and seeing how the head and tail work out. Eventually I should check. Alright, so it eventually filled up, but as you can see, as we go, after every third step we remove the item from the front of the queue, but we keep adding more, remove an item, add some more, remove an item, add some more, and eventually we add too many that we fill the queue up. While I was doing that, I must have had some wraparound because there were only 10 slots in the queue, and I was going up 0, to 9. That must have filled the queue. As soon as I add 10, 10 must be back in the initial position in the queue. If I wanted to, I could modify show to actually show whereabouts in the array each of those items was located, which would be a decent check. Well, anyway, that's enough to convince me. Okay, you can see that we've got some wraparound. Silly me, only printed out the location of the tail. But anyway, that queue seems to be working okay. Can anyone think of anything else I need to test? Underflow, dequeuing from an empty queue, I could try that as well. That should trigger an assertion. Other tests, I can't think of any. Alright, so that's enough with queue operations. I'm not going to bother writing the bank teller simulation, maybe I'll set that as a lab or something. Right, another type of queue which doesn't behave quite like the one we were just looking at, but which is used in a lot of different contexts as priority queues. Basically, instead of first in, first out protocol, it's kind of like best out, if you like. So it doesn't matter what goes in, but it's always the best or the biggest that is the one that comes out, the one with the highest priority. So items, there has to be a notion of a priority for each item. We could simply use the value and we could say, all right, let's take out the largest value each time, but it depends on the application. You know, if you think about operating systems, you might have processes that have got their own priority measures, how long they've been running. You can actually set a priority and you can take all that into account. You can compute a number for each process and then you pick the process that has the highest number, and that's the one that's taken off the queue. So priority queues, they effectively have DQ, NQ and DQ to make them look different to a normal, to a FIFO queue. We'll use join and leave. And an additional operation that you might be interested in this context is if you want to get away from the protocol altogether of always taking out the highest priority item, you might want to remove a particular item, this time identified by a key value. So remember that all through this discussion we're kind of talking about the notion of a collection of items. Items generally are structs that contain a number of different fields, and in particular they have one field that usually uniquely identifies the item, and that's its key. So we can say, I want to remove this particular item rather than just taking out the item with the highest priority. And we have all the standard operations, create a new queue, drop it, blah, blah, blah. So how do we define highest priority? It depends on the application. Sometimes we may be interested in taking out the largest key. Sometimes we may be interested in taking out the smallest key. If our priority was based on a timestamp about when the item was added, and we always took out the item with the lowest timestamp, then we would have just implemented a regular queue. If we used timestamps and we took out the item with the highest timestamp, we would have just implemented a stack, always taking out the last thing that we added into the queue. But as it says down here, the priority order might involve other things apart from just the key. So here's an example of priority queue. So we add 6 to the queue, goes on the end if you like. When something leaves the queue, depending on how you implement it, there's a number of different ways you can implement this kind of thing. You could arrange the items in priority order so that you always take the one off the front, or you could just put them in the queue as they arrive, and then when you come to leave the queue, you've got to scan through the queue and find the highest priority item. So when we do a leave here, we look for 25, that's the one that gets taken out. Then 15 becomes the highest priority item. If we do another leave, we're going to take 15 out. Add another item to the queue, it just goes into the queue. When we do a leave, the highest priority item 10 will go out, and then 9 becomes the highest priority, and so on. So this is just an abstract view of the way things are working. The actual concrete representation, possibly this could be an array, where we're just storing things in the array, and we have to scan through the array, find the highest priority item and remove it. And if we're going to do that, then we need to compress all the other items around the spot where we just vacated the highest priority item from. So what's the interface going to look like? Well, we're going to have a standard priority queue data type, items and keys, and those kind of things, those kind of operations there. How we represent priority queues, the actual data structure that we use, can have an impact on the costs. Here I've included as one of the costs the amount of space that's required to store the data structure. So most of the time we've been talking about time, counting how many times a particular operation occurs, and that's a measure of how efficient the program is. Often it's useful to also consider the amount of space that is being occupied while you're executing the algorithm or while you're representing that data structure. So when you have an array, you have to initially say, I want this many slots in the array. Maybe you never use that many. Maybe you fill it up and then you end up with errors. In either way, the amount of space usage for that data structure is constant over the whole lifetime of the object. So you allocate the object, you allocate a certain amount of space, that amount of space never changes. Of course, in the case of lists, you add nodes and you add nodes and you add nodes, so the amount of space changes over time. The amount of space used is proportional to the length of the list. That's all that's saying, or proportional to the number of items in the data structure. Heap is an implementation strategy for priority queues that we'll be talking about later in the course, but as you can see, it's one of the better queue representations. So with a sorted array, adding an item to the array means you've got to put it in the correct location, you've got to maintain the sorted order, and the order n comes from basically from the fact you've got to scan the array to find out where the location of the new item should be. Leaving, in the case of a sorted array, becomes dead simple. You just pull the item off the end of the array. So if you always arrange it so the highest priority item is at the end, you can just grab that when you do a leave and subtract the counter for the number of items in the array. Checking is empty, well that depends on the representation of your priority queue, but if you keep a counter of the number of items, then it's always order 1. With an unsorted array, you can see that you're swapping the cost of join and leave around. Join becomes simple, you just add the new item onto the end, but when you want to remove an item from the priority queue, you've got to find the highest priority item, which involves a scan of the array since it's unsorted. And similar kind of idea with sorted and unsorted lists. Priority queues turn out to be useful in a lot of contexts. One place we'll see them again is implementing graph algorithms, where no, it's 11 o'clock, I won't do that. So let's have a break and I'll come back and talk about recursion.